The paper talks about a round trip time. What is that based on? And where is that?
The propagation delay.
From where to where?
From when you put something in at one point in the line. Like in the worst case, if you're on one end of the line, then the round trip is, you put it in here, right? And the signal will take some time to propagate to this host. So this host won't see it until.
But specifically from where to where? I mean, is it just from one host to the very next host on the thing, or is it from one host all the way down the far end of the network? Farthest distance, or
well, the round, it depends on the context. Like if they're talking about between two hosts, then they'll mean between any two hosts, which could be side to side, or at the worst case, at the very ends of the subnet.
Okay, but if the main ether segment is terminated, what?
Oh, they probably are talking. If they're talking about round trip, they're probably talking about something higher than that, higher level than that. So they're probably talking about a packet going back and forth. I mean,
they talk about it as if it was something that was commonly understood because they never explained it.
Yeah. Why don't show me after lecture, and then we can look at the context, and I'll be happy to talk about that.
Is there anything you can say about what's the difference between what they describe here and what we use today? Because we don't use tapped cables anymore.
Yeah. So we're just going over some quick questions over the Ethernet paper. I mean, today the Ethernet used to be just these cheap coax cables. Which were great because they were cheap and you could connect them up. The problem is that they don't the effective length of these cables at that point in time wasn't as long as people wanted. So what you have now are these Category 5 cables, which have very different properties, signal properties, and you use those to connect instead of using a shared coax cable. Yeah, and the other reason is, sharing, as you can see in the paper, one of the big issues was collisions, right? And so if you have single cables, then you can minimize collisions. You don't have collisions on the cable, right? Because they're just connecting two ends. And if you might have collisions if you connect a lot of these cables together in a hub, right? But the reason these things that D-Link and Linksys they sell where you connect things up, usually what they do is they make them a bit smarter now. And instead of being a hub, which just kind of connects everything together with just physical connections, they use what's called a switch, which actually is a little bit smarter and can actually route packages. So you can have, if you have a four port switch, and you have two of the hosts talking to each other in these two, you're not going to get collisions between those communications. So if you see, when you buy one of these things, the hubs will be cheaper because they're basically dumb. But the switches are a bit smarter, so they'll be a little bit more expensive. But these days, all of that's so cheap, you might as well just buy a switch.
So is that how you? So how do you accommodate so many hosts to the same cables, or like you have like?
In the same cables.
Yeah, I mean they talk about in the paper how they cannot connect very many hosts to one of these cables. There's too many collisions.
Yeah, and that's one of the. If you have a switch, like if you instead of hubs, if you have switches, which means each link can operate pseudo-independently. Like if you can have multiple conversations happening at the same time without collisions. That's one of the ways that you get around having a lot of collisions. But if you're talking, I mean, if you're having a three-way conversation between three people, even on a switch, you can still have collisions there between packets. And so some of these switches will have a little collision light you'll see blink every now and then when you get collisions between conversations. But the switch is smarter, so it doesn't just connect everything together into one big effective ether cable. And these days they're very cheap. Back then they really didn't. They were using this coax instead.
So the Ethernet, that protocol, is this what's used today for all the?
Yeah, most cards these days use Ethernet. There was what did IBM have? Something called a token. What's the token ring? Yeah, they had this thing called a token ring, and the idea there was, the very high-level idea was instead of having to try to prevent these collisions, you had some kind of token that allowed you to control the resource, and you'd kind of pass this token around, and so and that's how you controlled for collisions. But the Ethernet just took off much faster and better than this token ring thing. The token ring, I believe, was proprietary, though. Maybe Stallman would know, but I don't know for sure. But the Ethernet, I don't know. I remember that was developed at Park by Bob. Well, you guys saw the authors, Bob Metcalf, who has a beautiful townhouse over in the back bay here, and and I don't remember about what happened to the other guy, but this was developed at Xerox PARC, which is a research lab. So it was published, and it was at that point it was open, and they weren't patenting a lot of things, and so that's probably one of the reasons I suspect what it became so popular.
Although this is not what they use for transmitting over the internet. This is only for like local area or wide area networks, right?
Yeah, I mean, this is what they use for, usually for subnets, like your local subnets. They definitely don't use that for these big haul, these long haul trunks over the internet. And if it's if it's something like fiber, they definitely don't use anything like this. You want to stage things as well as pre-stage things along these long haul networks, especially because if it's a long cable, then the propagation delay would really interact badly with the collision detection mechanism.
So what's the protocol for the long cables?
It varies. I mean, in the there's, I think that some of the cooler ones for these fibers, I mean, they do all sorts of multiplexing. They do frequency division multiplexing, and they have lots of different frequencies of light. And then they send bits encoded as, you can send bits encoded as, I actually don't know how they particularly, but you can imagine they can encode them as phase shifts or as the absence or presence of a particular color of a particular frequency. That research is going so fast. I mean, I haven't kept up with it at all. But there's a lot of good stuff on that out there.
You say that's used for subnets. I'm familiar with Ethernet being used commonly, like for a university network or something like that. But would it, for example, with you've got a cable modem connection at your home, and I know you use an Ethernet card to connect to the cable modem.
Right.
But from there, is it still using Ethernet?
Unlikely.
Would that be considered a subnet, or is
they would? It's unlikely that they would be using it just because of the infrastructure. There's actually there's companies that are out there that build infrastructure specifically to handle that type of traffic. There's these things called head ends that you build where you distribute out. You take a big trunk comes in from the cable company and kind of distributes out the data. And there's a lot of work being done there to try to squeeze more data out. There's all sorts of issues because that cable that comes in also has all the TV signals. So you can't. I mean, you don't want an Ethernet-like protocol on there unless you want a lot of occasional static on your TV because of these squelches that you put on. So that's one of the issues that they face. Now, one of the things you could do is you could actually piggyback an Ethernet protocol on a frequency that's outside of the range frequencies outside of the range that's being used by the TV. But I mean, in a sense, sometimes it doesn't make sense to do that because if you're especially in the last link, there's one cable coming from someplace coming to your house, right? And it's just a point-to-point link in that sense from some head end or equivalent to the cable modem. So the Ethernet protocol is it's more interesting when you're sharing some medium, when there's a shared link to communicate over. And if you guys noticed in the paper, it was they referenced the Aloha work in Hawaii, and so they saw that. I mean, that's part of where they got this idea was, if you're transmitting EM over the airwaves, it's in essence a shared coax cable. It's the same kind of medium in a sense. It's a broadcast medium with propagation delays, with signal degradation over distance. So they took that idea and converted it into something, implemented it in a different medium. Okay, are there other questions about this Ethernet paper? So the last time we were talking about network layering, and we talked about how we can take these 7 layers of the OSI network abstraction and condense them down into 3. So we talked about the link layer, which is about actually getting data from one point to the next. And we talked about the network layer, which implements getting data across a network. And for the internet, the network layer provides something that's very simple, like it's just sending datagrams, best efforts. We talked about what that means. So now let's go up to the next layer up, which is the end-to-end layer. And this is representative of the 4 other layers that we saw in the OSI, the 4 highest layers. So what is this layer about? It's about implementing more functionality or more apparent functionality on top of an unreliable network layer in our case. Now, what we do there is, depending on what our end application needs, we can do things like try to compensate for latency, try to do something about ordering of messages or datagrams or packets, depending on what layer you're talking about. You can do something like adding more checks to improve data integrity. You can try to improve routing accuracy, though you have to be careful with that because you don't want to violate the abstraction the routing abstraction below in the network layer, at least not without good reason. And one other big thing is you might want to add security. Now, not all applications are going to need all of these, so what you end up doing is creating a set of transport protocols to help to use depending on which application, what your application's requirements are. So transport protocols typically send messages or streams across the network. I'm going to use the terms messages to refer to a set of data that at the end-to-end layer. And messages, think of messages as when you hand that message down to the network layer, it can break it up into datagrams, which can be then broken up into packets by the network. Now, when you have these transport protocols, the sources and destinations on these are hosts attached to the networks. So you're sending a message from one host to another host. I'm sorry, one level above that. The sources and destinations are actually applications running on hosts that are on the network. So if you have some network and you have some host here, someone here, remember at the network layer you think about sending datagrams from here to here. At this end-to-end layer, you think about the applications that are running. So Netscape and AOL server. Netscape is going to send a message to an AOL server somewhere else, somewhere out on the network. Okay, that's the level of abstraction that we're at. Typically, the way these things work is that there's an abstraction called a port. How many of you guys have heard of this, of ports? So machines will have, well, if you go to like your Linux machine, you'll see there's a file in there that lists a bunch of ports and a bunch of services. So there's things like HTTP, and there's things like UDP, and there's SMTP, and these are all these different, they represent different types of applications like Netscape and your some kind of mail and so on. And what you do is that you agree upon certain ports being the place where you listen for sending or receiving a message. So that's how you know that this message is supposed to go to a particular application. So if you send something to port 80, does anyone know what port 80 HTTP. So port 80 is typically where you talk HTTP back and forth. What's FTP? 20, is it 23? 23, FTP is 23. I think it uses another one too, potentially, depending on the type of FTP, which is what you use to transfer files around. What about email? Like SMTP, 25 is SMTP. So what ends up happening is when a server, for example, when you start up a server like AOL server, it goes to the operating system and it'll say, okay, I'm a server and I'm going to be listening on port 80. So operating system, whenever you get a message coming in at the network layer that's addressed to port 80, give it to me, and I'll deal with it. And that's how. And similarly on this other side, when AOL server sends something back, right? Netscape here can be listening, or we'll be getting that message back because of the way the ports are addressed. So what is this? What is a send or receive, a generic message send or receive protocol look like? Well, the send is going to have a destination address a destination port. So together the address and the port refer to an application running on the other side. And then you want a reply port so that this thing knows, you know, what port is to reply to over here so that the proper application, the client gets it. And then you need the actual message itself. Now, one thing that isn't in that interface is the source address. Why do you think that might not be? Why do you think that isn't necessarily needed as part of a send type interface? Yes.
If you're just
Sure.
forwarding in a protocol, you don't really want to be adding your...
Okay, if you're sending something, you don't necessarily, but what if you do want something to come back? Which in this case, you know, an HTTP request for a file, for some file, which then you expect to come back. You do have the reply port, right? But why wouldn't you want to put that? I mean, you could put the source port, the source address in there, but do you think that's necessary? Yeah, that's right. The lower layers know you know what your source address is. In fact, when you're writing this code, it would be redundant for you to have to grab this source address all the time, and so that's typically included in the lower layer. So when this guy receives it, the lower layer will tell him, oh, this is where it came from. And that's always, if you're assuming you're on the same host over here, then you let someone else manage it. If you're on a mobile host, then it's even better to let someone else manage it because you might not know. You don't want to be sitting there having to deal with where am I right now before you send every message. So the general receive interface is typically something like accept, and what you get is input to that is the source address, which is given to you computed by a lower network layer. The source reply port and the incoming message, both of which were part of the send. Now, one of the ways that you can implement this is by what's called a callback procedure. And so what happens is that AOL server will say something like, here's my callback procedure, and it'll give that to the operating system, and it'll say, it'll tell, here's the port that I want to listen to, and it tells the OS, whenever you get a message that comes in on this port, call this procedure, and that'll transfer in my process. Bring up my process, call this procedure, and I'll do the right thing. So why would you want that type of mechanism as opposed to what's otherwise known as a polling mechanism, where you sit there and you go and ask the operating system every time you get switched in, is there a message? Is there a message? Overhead. Very good. So the thing is, in order for AOL server, for example, to explicitly check each time, it has to be swapped in, right? Or there has to be a context switch for it to do that. Much easier, much better if it just sits there, wherever it is, and does nothing until a message actually arrives. And the reason I bring up that point is because from a scalability point of view, I have a friend who actually, I'll use instant messaging as an example. He did an instant messaging startup that was later sold to Microsoft, and one of the techniques they used was they said, well, if we sit there and we poll all the time, which is what typically, if you just think, well, what's the easiest thing I'll do? I'll just poll and wait and see until something comes. The overhead associated with that would just end up killing you. This doesn't allow it to be scalable. There's just all sorts of bad scalability issues. But by doing this more event-driven or interrupt-driven type style, where you get called when something actually arrives, it allows for the server to handle a huge, order of magnitude more traffic.
What would be the advantage of polling?
The advantage of polling?
Yeah, like why would? That's a big cost, but why would anyone choose to do that in the first place?
Oh, ease of implementation. Like this whole callback scheme. Callbacks is something that's not that. If you're a beginner programmer, you probably is something that seems a bit more complex than what you're used to. And as you become a better programmer, then it becomes very intuitive, and you start using them all over the place, and you love them. But if if you're just someone who says, oh, I'm going to do an instant messaging internet startup, and you don't have a lot of coding experience, you might decide, oh, this is easy. I just do a polling loop, and then whenever something comes in, I just handle it. So this is one of those nuggets that, like, that if you have someone, someone taught me, someone, I'm teaching some of you guys probably have done this a lot of times already.
Callback system, something's polling, right?
Not necessarily. It depends on how the operating system handles interrupts. So you can imagine down in the lowest layer, you have at the link layer, right? The Ethernet card gets some incoming message. Well, it can raise an interrupt, which then the processor will go out and handle. So we were talking about messages before. What about streaming? So here we're starting to get into the question about connections versus not. In a generic streaming protocol, you do have this idea of a connection that you open and close. So you'll open a connection. If you want to receive data, you'll open a connection. And what that does is it has a destination address, so somewhere else it's going to feed you that stream. Once you open that, what you'll get back is some identifier that says, here's how you get access to that streaming data. And so that's the equivalent of opening, of setting up. And then there's also the notion of teardown, which is close. Now, if you're the server and you're going to be writing that data back, there's going to be some notion there of a stream ID that you just write data to. And whenever you write data, it just flows over. The network layer gets it, and boom, it sends it over. Now notice that the writes here don't require a destination address. Why not?
We've already opened it, and then the protocol is going to keep a hold of that when it's creating packets to send over IP.
Yeah, so in essence, remember before when we were talking at the lowest layer that there was this notion of state that you had to keep if you were thinking about connections, which was, in terms of the asynchronous network, which of the, if you're doing time division multiplexing, which of the pulses was actually yours, and you kept that. In this case, we're at a higher layer, but we still have this state that we're keeping around, which is for this stream ID, where's the destination host, where's the destination port? And so you would expect that streaming all the way down, this would be the case, that state there would be state maintained. So when you write something, it would just be forwarded by the protocol the implementation would manage that forwarding, for you. Okay. Now the read interface, there's lots of different ways you can imagine getting a stream ID. One of them is to go out there and say, I want a service, I want this particular type of service, like video or Windows media, and here's the name of the thing. And there can be some name resolution that happens behind your back that gets that. So, this is like, I want a real video stream that has, that's this video of whatever in sync. And that'll give you back a stream ID. And then what you do is you can just call, get more stream data to suck this data out. And then you need to know when the end of that stream is. So one of the reasons you might want to explicitly use this get more stream data instead of some callback is that you may only be able to handle the stream data coming in at a certain rate. So if you want to, for example, grab enough bits to create a video frame, then you can sit there and get the data, and then when you have one, you do a computation and you render it on the screen, and then you say get more stream data and try to get the next thing, and you can handle at that level whether there's some frames that are missing and try to adjust there. So this is one reason why you might not want to call back if you're in the middle of getting a stream. There's probably something that's computationally intensive that you want to be able to manage a bit better.
Somewhere there has to be a buffer that holds whatever's coming in.
Right. Right.
Is that locally?
It's probably, well, there could be buffering anywhere throughout the network, but there's probably, if I were doing the implementation, I'd have a local buffer also. And if you look at, if you have these applications, these real applications and so on, you'll notice that if you go into the options, a lot of these have some kind of buffer that you can adjust. So these buffers can actually be exposed to the end user. And especially in something like a video application, you might want to buffer lots of data, especially if you get it in bursts. So you might want to increase that buffer size, but in something like video, if you're getting high quality video, it might be megabytes of buffer that you want. So that's one of the reasons why it might be exposed to a user, is that it might, increasing that buffer size might decrease your machine performance because you might have to swap.
The time that we pull in the additional data, we have to put it someplace to store it while we're dealing with it.
Mm-hmm.
So we have to have an internal buffer, and this is going to require us to have kind of a slightly more external buffer.
Yeah, well, there's an application level buffer, and then there's the natural buffers that you get from the operating system. So the operating system itself will buffer data that comes in, network data that comes in, and it has its own buffering scheme. And there's some. If you go into the Windows registry, you can change some of these parameters and have it allocate more or less. This is especially important when you're on a modem or on a slow connection. You can actually adjust buffers even all the way down to the chip that sends the signal back and forth. There's some adjustments you can make as to how big its send or receive buffer is going to be. And the reason those kinds of things are exposed, even though it's a lower layer to the user, is because they can have a huge impact on performance. In the video case, the end user buffer is huge. It's something so big that an operating system would never allocate something that big. It could be megabytes depending on the quality of your video. But the end-to-end argument comes to play here, which is that you don't want the operating system or the lower layers having this huge buffer just because in case you get video, because then everybody else has to pay that price. Does that make sense?
It does, although intuitively it seems like the external buffer, the one that's outside of this get more data stream, it seems like that one would have to be larger because that one has to wait until we decide to get more data.
That one has to
store everything until we decide to get more data.
Right.
So
it
seems like that's going to have to be at least as large as the internal application buffer.
And it depends on the specifics. So for example, if you were doing some kind of voice and you were on a gigahertz processor that wasn't very loaded, you could probably process the voice very quickly and you might be able to grab it as fast as it comes out and do something with it. But if you're doing this high-res video on a Pentium or Pentium 2 even, then you don't have a lot of hardware support, then you might need the larger buffer. So the buffer size is going to be dependent on the bottleneck in the system. And if the bottleneck is the processor, then you'll have to increase that buffer size. If the bottleneck is the network, then your buffer doesn't have to be as large. So let's look at some more real examples. There's a family of IP, of mumble IP. So IP is the network layer that does the internet protocol. That's the layer that you give a message to get it from one end of the internet to anywhere else on the internet. Now built on top of that, there are some protocols. So UDP, TCP, and RGP are three protocols that are built on top of IP. So you've heard TCPIP. That protocol, TCPIP, is actually two separate protocols at different layers in the network framework. So UDP, here what we're doing is adding the notion of ports and adding a level of data integrity, and that's it. So this is a very bare bones type of protocol. So this is all this protocol really allows you to do is do very simple application to application communication on top of IP. So remember, IP will just get something from one host to the other. That's the layer at which it sits. UDP, which sits one layer above that, thinks at the level of applications and therefore introduces this notion of ports. This is what on top of, the data integrity. This also does an extra little bit more data integrity checking. So it does another checksum. Now remember before the link layer did a checksum. Remember that how we said for so many bits it's going to do whatever 8-bit checksum, whatever it might be. To check data integrity. This one adds a level on top of that. Now, why is it a good idea to add a little bit more data integrity checking on top of that if the link layer is already doing something? Is that totally redundant, or are there some places where the errors can occur that one might check and the other might not? Okay, well, the UDP packet header, if it's being transmitted by the link layer, anything that goes from one link to another, there's checksums against it. So anything that's that's data that the link layer receives, it's going to say, I'm going to compute a checksum over the whole thing, whether it be pack header or payload or whatever it might be.
So you check any...
Go ahead.
The article said the data from memory in parallel form wouldn't have been checked.
Okay, good. So there's the switches along the way. Right, remember these guys have to, in the store and forward network, like we talked about before, there's buffering that happens. There's, at the network layer, you can have a datagram that's broken up into smaller packets that are sent, and during the process of breaking them up, there could be data corruption. So there are stages along the way where the link layer isn't involved at all. Doing a little bit more of data integrity on top of that at this layer takes into account all of these different steps that happen that are not explicitly part of the link layer.
Is that just the passing up and down between layers of abstraction? Is that what you're talking about?
Yep. That's it. So one of them is RTP, which is a real-time protocol that's built on top of UDP. And there, the idea is you add timestamping. UDP you would think is basically everything you need for streaming, except that you want to make sure that you can order these packets when they come in. So if you're sending a video, one video frame and another video frame, you want to make sure you put them in the right order. The timestamping helps you do that. Now there aren't any other integrity guarantees. They just uses whatever UDP uses. There aren't any reattempts to send packets that didn't make it. And that's because, like we talked about yesterday, the nature of streaming is that if you miss a packet or you miss a message, by the time you get it back, it's probably too late. You're already several frames more into the video or audio stream. TCPIP has a lot of guarantees on the messages that are being transported. Again, it sits on top of IP, the network layer, and it has some guarantees. So messages have to arrive in the same order that they're sent. You can't have missing packets. You can't have duplicate packets. I'm sorry, this should be missing messages, duplicate messages. There is some extra error checking that's being done, and there is some flow control. And this is what you use when you want something that's more reliable, when you want to do something like HTTP, or when you want to do something like having a session between two computers. You probably want something that has these types of properties. And so TCP/IP is a generic transport protocol that you can build other protocols on top of that need all of these types of properties. As you can see here, there's all sorts of overhead involved in TCP/IP that you may not need if you're just thinking about streaming or something more simple like that.
So is the TCP not dealing with packets, but only looking at the message?
Messages, that's right. It's looking at a message. So you give TCP a message, and then it gives it to the network layer, and the network layer says, either I'm going to send this as one datagram, or it can send it as multiple datagrams. It can do whatever it needs to.
Between packets and datagrams?
Yeah, packets I'm using to refer to the lowest layer, the link layer data, and then datagrams to the network layer data, and then messages to the end-to-end user data, layer data. That's why I used the wrong term here.
But UDP talks about datagrams, and yet it's at the lowest level of PDE.
Yeah, that should have been messages.
No. Just the meaning of D in UDP. It's not you. It's just what does D mean in UDP?
Oh, yeah. I'm just using this terminology so that I can try to keep layers the level that I'm talking to straight, so that we know when I say message we're talking about the end-to-end layer and so on. But yeah, I should be careful about that. Okay.
End-to-end layer is above the network level?
Yes. The network layer, IP, is the protocol that's used at the network layer for the internet.
And TCP, UDP, those are all end-to-end?
Yeah, those are all at the higher.
Same thing, end-to-end layer, transport layer?
At the transport layer or above, like HTTP is a couple layers above that, and built on top of things like TCP/IP. And one thing that you'll notice is that when you send things across the internet, right, even if you're on a Microsoft type of network, you're still able to interface to the internet. But what you'll notice is that usually there's some kind of difficulty in trying to merge both of those types of networks unless you have some box or something sitting in between them that talks both of those types of protocols. And even then, the semantics of the protocols may be different enough that you can't have all the functionality back and forth. What you do at times when you want to merge these networks is that you'll have some kind of piggybacking or encapsulation, where if you wanted to talk the Microsoft protocol across the internet, you'll take what the Microsoft, all the information the Microsoft protocol needs and stuff it into a message, and then give that to TCPIP and have that be sent, and then it gets decoded. That gets decoded on the other side is, okay, now I've got my payload for my TCPIP. Now let me break that up into my Microsoft, style protocol, and then let me do something with it. So that's why you can do things like if you're on one side of the internet and someone else has network sharing, drive sharing available on the other side of the internet, and you're both on Microsoft machines, if you know their IP address and they haven't protected their shares, you can access it. I actually read a story recently about someone who's making a Napster version of this thing that goes out and figures out who's got unprotected Microsoft shares available, and it gives you this directory, and then you can just go in there and it'll give you files, so you can search for file names and stuff like that, and you can actually connect to the machines and do anything.
By default, that's everyone using Windows everywhere.
Is it on? I thought file sharing wasn't on by default.
I'm pretty sure it's on by default.
Really?
On some versions.
Because these guys were arguing actually that one of the, you can imagine they're in all these legal issues. And one of the things they argued was that it wasn't on by default. So they argued that someone would have to intentionally, their argument was you would have to intentionally turn it on.
The paper actually says under certain cases it's on by default, but only if they turn on a certain networking, which I understand.
Yeah. So it takes explicit action. What's that?
They're not routable by default, so you have to have somebody routing those packets, or they won't get beyond your local network.
Yeah, and in fact, that's an interesting point. Something like Media 1, they don't route those packets at all coming out of the port that Microsoft uses for security reasons, because when you're on something like Media 1, even though it's not Ethernet, there is some sense of having a shared segment. So in theory, if the ports were not blocked, you could actually look at your neighbor's files and if they had their shares available.
How does it work this thing with messages arrive in the same order as they're sent? Because I guess two messages could be sent in different routes or whatever.
That's right. So one of the things you can do is have a sequence ID that you put as part of the header for the message. And so at the receiver side, the TCPIP implementation will look at the sequence that comes in and say, okay, well, if I got message number 1, message number 2, and message number 4, then I have to wait until message number 3 before I deliver message number 4. So it can at the receiver side, it can wait until it gets the next element in the sequence, and if it doesn't get it, then it can go back and say I didn't get it, resend it to me. But what happens, all these properties here, what you see if you're on top of TCPIP. So if you're on top of TCPIP, you shouldn't expect to get any duplicate messages. Right? If you got a message once, you shouldn't expect another one to just appear. The TCPIP implementation should just not even send it to you if it receives a duplicate. Okay. Yes?
Just a question about the flow control on this level. That seems like something that should be happening at a lower level. I was just wondering what that, why the messages can wrap and stuff.
Yeah, it is. That's a very good point. A good observation is that there is somewhat of an abstraction violation here. And we're going to actually, the last couple slides are going to be on flow control itself. So we'll get into that. But there is somewhat of an abstraction violation. Usually when you see an abstraction violation, if it's for good reason, it tends to do with performance. And in this case, you'll see that there are a lot of performance issues. You can do flow control at various layers in the network, and we'll see how it's done here. Flow control. It's how you control. It's a way of controlling congestion. So let's think about some of the about the implementation of some of the different types of semantics that we had talked about before. So remember we talked about at least once delivery. If you have an at least once delivery protocol, what you're in essence saying is that the message will get through to the receiver. At least one copy of the message will get through. You might get duplicates, but there'll be at least one. But let's think about that a little bit more. So the message can consist of one or more datagrams. The datagram header, in this case, will contain an ID or some kind of identifier that says here's that differentiates the different datagrams. Now, what the sender will do is give this datagram or message to the network layer, which divides it into datagrams. And then it'll wait for an acknowledge. And then it'll retry after a timeout. So let's think about how that would work. So here's a datagram. And what you do is you send it over, the sender and the receiver. And you send it over here, and then the receiver says, OK, I got it. Right? Now what this is what's called the lockstep protocol. So in this case, you send a datagram, you get an acknowledge back. You send another one, you get another one back, and so on. OK? Now, this will work fine from an at least once delivery point of view, except you have to assume that the network is reliable, that the network itself will get the message eventually to the receiver. And yesterday we learned that the internet, as one example, is not a reliable network. It does best efforts, but it could run into congestion or some other issues. So you're not actually sure that this message will get there. So that's actually why you need this acknowledgement. You need the acknowledgement to make sure so that the sender knows that it was received. And if there's a timeout period on this, if you don't hear back from the receiver after a certain amount of time, you can just resend it. And that means that there could be several copies of this that go through, because actually the acknowledgement might get blocked. Oh, question? OK. Now, one question is, what timeout period should be used in this type of scheme? And you can have a fixed timeout, and that's simple but not optimal. And one of the reasons it's not optimal is that, guess what? Traffic patterns on the internet change. So if your timeout, if it turns out there's congestion and the packets are going to take a little longer to get from the sender to the receiver, then you want to make sure that your timeout isn't too short, such that you keep sending a bunch of duplicates because your timer keeps going off. You want to make sure it's not too long, such that you send something and then you're sitting there. The receivers, could be sitting there waiting for something, and just you both could be sitting there waiting, and nothing ever happens for a long, long time. So there's some, like in the Ethernet, you read about this exponential backoff algorithm. You can do a similar type of thing here, where if the timeout that you're getting doesn't seem to be right, because you either don't hear, you realize that you're sending too many because you're getting too many acts back, or that it isn't working because it seems like your timeout is too long, you can readjust exponentially to try to get very close to a more optimal timeout as soon as possible. OK. An acknowledgement. When you see in networking papers, that typically means an acknowledgement for something that was a message that was sent. So another way to do this is to have the receiver use what are called negative acknowledgements. Now, in this case, what you do is each datagram has to have some kind of sequence number, so you know whether you have all the datagrams in a message or not. Now, imagine that you're the receiver and you receive 2 of them. Well, what you can do is send back a negative acknowledgement and say, oh, for this message, I need you to send me back the second in this sequence of 3, or these 5 different datagrams in the sequence of 100. And you send that one negative acknowledgement back, and then when the sender receives it, they can send those. They can forward only those datagrams that are missing. Now, the nice thing here is that we're having one negative acknowledgement being sent back per message. So we have a little bit of an optimization in that we don't have to have all these acts. We don't have to have there to be one potential acknowledgement per datagram. Instead, what we have is at the receiver side, they just send one NAC back when they're missing things. Now, you also have to have a timer here, because at some point, if you're supposed to receive 15 datagrams, and you say, okay, well, when do I send the NAC? How long do I wait before I send the NAC? So there still has to be a timer, so the timer issues are still around. But the delay that you get in completing this is now per message instead of a per datagram. Mm-hmm.
Is there a timeout going the other way so that it knows to send another NAC if it doesn't receive the datagram in a certain amount of time?
Yeah, and it's funny. This is one of the reasons timers are actually they're a necessary evil in some sense. Is that when you use timers, you start getting into these things like, well, do I have to send an ACK for the NAC, and how long do I wait for that thing, and then what about an ACK for the, and so you can get into all this complexity just because you're timing out on things. But that's sometimes you just have to bite the bullet and just do this a couple levels, and at some point just give up and say, failed.
Do NACs get X?
In some systems they do. Because when you send the NAC over, it'd be nice if you got an ACK back saying, okay, I got this, expect the NAC, expect the datagrams to be coming. This is a great setup for what's called the two generals problem. And this was framed by a guy named Jim Gray. And what he basically said was that there's never going to be 100% guarantee that a message is delivered, no matter how many of these ACKs and NACs and so on that you use. And so the question is, imagine, this is a little militaristic. So there's some city here, and imagine that there's two generals, one sitting over here with his or her army, and one sitting over here with another army. And the idea is that this city is powerful enough to repel an attack by either one of these. If either one attacks, boom, gone. But if they both attack at the same time, they can take the city. Okay. Now, how would you expect that these two will coordinate? Well, they probably will have some runners. That this one will go and send a message over here saying, let's attack tomorrow at midnight. And then this one will come back and say, got it, tomorrow at midnight, all set. Now the problem here is that these people in the city aren't dumb, and they know that these guys are going to be doing this, and so what they have are a bunch of snipers sitting around, and whenever they actually can prevent runners from going back and forth. So it's Jim, just go with me on it. So what's the problem that can arise? Well, imagine that this general sends a runner out, okay, but never hears anything back. What are the two possibilities? Right, either here or here. Right, and the thing is, if this general does receive it, and knows that his or her runner can get nailed, is he going to attack before he gets something back? Probably not, right? Because if you attack and you don't know if the other general has done anything, then you could destroy, your whole army could be destroyed. So the question here is, when you have unreliability, how do you coordinate these two to make sure that these messages, to make sure that there's this 100% guarantee that a message was delivered? And it turns out that you can prove that there's no way that this could be the case. Because the way you prove it is you say, suppose there was a way that you could do this where you're sending ACKs or NACs or whatever it was, completely reliable, that would guarantee that both of them were coordinated. Well, if you take that algorithm and say that there's n steps in it, runners going back and forth, because of the unreliability of this network, you always have to assume that any one of these could get squashed. So let's say that this one was squashed. Right? Then this algorithm, what it implies about this algorithm is that all you really needed were n-1 steps to guarantee that they were both coordinated. And then if you go back to if you reduce that all the way down, it shows that, there is no algorithm, because at the end point, you're back to a situation where there's only one step, which is one runner going, and that there's no solution to that. So given that type of argument, I mean, it proves you can't, with an unreliable network, coordinate like that, or assure at least once delivery. Now, what you can do is you can try to make reduce the probability of failure to something very small. And how do you do that? Well, one thing is, imagine if over here, if you get, all of a sudden you get 10 runners, and they all run out at the same time, and you hope that at least one of the 10 will get through, right? And depending on the distribution of the unreliabilities here, you can calculate what the probability is that one will get through. So the more that you send, right, the higher the probability that at least one will get through. And so by knowing something about some of the statistical properties about the network, you can actually decide how many of these you're going to send and in what order and how you're going to stage them to reduce the probability to something that's very small. And it could take, the trade-off is that it could take a lot of resources, including time, to get to that. But that's really the only real optimization you can do which could work very well in practice, because if you can get the probability down to less than, say, the probability that an electron is going to destroy a cosmic ray is going to come and disrupt your whole chip, that's pretty reasonable. I mean, you can assume that if a cosmic ray is destroying your chip, that you've got other problems. With that said, let's talk a little bit about end-to-end performance. One of the problems in a network, as we saw before, was congestion. Right? So congestion. Who can tell me what congestion was? Who was here yesterday?
There's a lot of packets flying around. It's very difficult for your packet to get through.
Good. So there's so many packets coming in that you're overflowing a buffer in one of these packet switches, and what does a network like the internet typically do when there's congestion and it doesn't have any place to store all these incoming packets? Drops them on the floor. Boom, gone. So that's bad. So you want to be able to, one of the things you want to be able to do is, to get better end-to-end performance, is to somehow control how these packets are going through the network, and in a way that minimizes the chance that you're going to have congestion along the way. Or if you do detect congestion, that compensates for it. So one thing that you can do here is somewhat of a lockstep protocol. Boom, 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 boom. And this is nice. It's simple. It's effective, but it is too much time. You're going to waste too much time waiting back for the acknowledgement each time, going back and forth. But what it does give you is that you send one. You're going to be sending, if you take out the ax here, you're going to be sending at a rate, right, that the receiver can receive at. Right? That's the whole point of trying to do this, to maximize the rate that you're sending to match the rate that the receiver can suck packages in at. So the problem with this is that if you keep going back and forth like this, you get into the performance issues are bad. So how do you get around some of these performance issues so that you don't have so many ACKs, like one ACK for every datagram? Well, what you do in that case is you do what's called windowing. And instead of this here, what you do is you send a set of datagrams at once. Now, a set of datagrams, in this case, there's 4 of them. That's your window, basically, is these 4 datagrams. And then what you do is, but you don't wait. You send the next datagram before the acknowledgement comes back for it. So you send these 4, boom, 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 and at some point, you'll be getting acknowledgements back. Right, but now look at what happens. How long does it take to transmit these 4? Well, you go boom, 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 and then by the time you're already starting to send these other ones, you're already receiving acknowledgements. Right? So in essence, the time that it's going to take you is the time that it takes to send those, plus the time that it takes to receive the last acknowledgement. Right? So that's a much better, yes?
Why don't they just send one ACK back saying they received the whole window, or one NAC saying we received the whole window except for number 3? Yeah,
and that's a good optimization. You still end up getting the same time if you get this one at the end back. It's still the last. It's still the however long it takes to get these over, plus the reply time for the last packet that comes back, which could be a NAC.
So what we're primarily concerned with here is not minimizing network traffic, but minimizing latency time.
Minimizing drop packets. What you want to do is minimize the amount of packets that get dropped.
This isn't going to minimize any drop packets versus the lockstep.
Oh, so this is an optimization over that. So the lockstep.
It's still going to have as many drop packets, though. It's just, and it's still going to have the same amount of network traffic. It's just going to have less time to transfer them.
Right, and that's the optimization. Is there's the thing that you want to make sure. Here, the problem you don't want to face is having these packets dropped at some point. So you want to start pumping them in as fast as you can. So the lockstep is one way to start pumping them in a way that doesn't get you these drop packets, because you get an ACK back each time. So but that's a very simple one that takes more time than it should. So here what we're trying to do is pump up the rate at which we send these datagrams out. So remember before we had this idea where we send when we come back, we send when we come back, and so to do 4 of these, we spend this much time, right? So we know that's probably, I mean, that's the simplest case, and we know that if we get some kind of congestion there, I mean, there's nothing you can do about it at that point. But what we want to do is that simplest case, we want to say, well, how can we increase the rate at which we're sending these packets and still not cause congestion? So we're starting off with the simple case, at which point the congestion isn't your fault, because you're sending only one thing at a time, and then you're trying to make it into a more optimized case where the congestion could be caused by you if you send these things too fast, and you want to find what the right point, how fast you can send these out at in order for you not to cause congestion. And make this a little more concrete, just so that make the point. Imagine that. Here we had a buffer size of 2 at this point in the network, and say the rest of the network was really fast. And at some point there was something that had a buffer size of 2. Well, if we're just doing the lockstep, boom, 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 one after the other, and we send something, if this is already congested, then we're out of luck. We can't do anything. But assume that there's no congestion here. Well, what we're doing is we're sending one, and then here, it gets read in here, and then it gets sent out. Great. Now let's say that we increase our window size to 2. Well, now we're sending 2, and boom, this fills up, and then it gets, because it receives 2, and then those go off. Now let's say we increase our window size to 3. Well, what's going to happen? Well, there's going to be a third one that tries to get in here, and the 2 spaces are already occupied. Boom. Now you're causing the congestion. And you're causing the congestion that's hosing your packets. So now what's going to happen? Well, if you have your window size of 3, then one packet of each window of each set of datagrams is going to get dropped each time you try to send this. So it's going to cause these NACs to go back and resends to happen. So the optimal case in this is to send 2 at a time, and each window size you send 2, and then you can wait for these to start coming back. So one of these can leave, another one can come back this way, and so on.
So who are we asking? It says sender asks how many datagrams can be sent at a time. Because in this case, it seems like it's some intermediate switchboard or something. Right. So this is why you basically need to have a more adaptive algorithm. In the simple algorithm, in the simplest version of it, you go and ask the receiver, because you assume the receiver is going to, you first assume, assume the network is not going to be congested. Let's assume the congestion is at the receiver side. So let's say that the receiver's on a modem and you're on you're the server and you're on a high-speed line, right? Well, that receiver is only going to be able to receive at a certain rate. So you can ask them, what is your ideal window size? And then, because the receiver probably has a reasonable idea of how fast they can receive these things. So you get that back. And then what you do is you use an adaptive algorithm at that point to modify the window size if it turns out that the bottleneck isn't over here on the receiver side, which you don't know. In that case, neither the sender or receiver in general will know where the congestion is here, or what it is and how it's going to change over time. Okay. So I mean, again, the way this works, you send several datagrams at a time before waiting for, and you send the next one before the acknowledgement comes back. And then
once you get the last acknowledgement back, and you get, in essence, this last one could piggyback permission to send another window, or that might be a separate one depending on the protocol. But before you send the window, you need permission to start sending again, because if the receiver is feeling congested at their immediate end, then you don't want to start sending another window immediately. Okay, so this. If the receiver, however, you can optimize two messages, combine them both into one. If when the receiver receives the last datagram, it's ready for the next window, it could immediately send back, piggyback with this ACK, if it's received everything, a request for another window. So then in that case, you start this thing again. Boom, 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 boom. Yeah. Yeah, this is your window size, so you need permission to send them back. If the congestion happens over here, the buffer, you don't want to overflow the receiver's buffer, because there you can actually have information. The receiver knows what its status of its buffer is. So if the congestion is in the network, you'll end up having to discover that. If the congestion is over here on the receiver side, the receiver can give you some initial value to say, here's what don't give me a window larger than this, because I'll overflow. Round trip time times the bottleneck data rate. Now, so the bottleneck can be a component or a link within the network. It can also be on the receiver side. But intuitively, there is, let's start off at the higher level, there is an optimal window size. Like we saw one here that was 2. And anything that's smaller than that is going to be less efficient, because you get more into this lockstepping. And this equation comes out of the fact that when you start throwing data onto the network in a sense is the data itself is living on the network and on the receiver, right? You can if you start staging packets into the network. So let's say you have, let's say the delay here is 1, 1, 1, 1, 1. You can actually have 1, 2, 3, 4, 5. Suppose that you send 5 datagrams out, 1 every second, right? There's going to be 5 datagrams living on this network before the receiver actually starts getting one. So that's why you take the round trip time into effect, and the bottleneck data rate is going to be how fast this one can start spitting them back out. And in this case would be a receiver, or in this case would be how fast this one can spit them back out. So let's take a more concrete example. Suppose you had something where you had this type of network. Let's put another one in for fun. And suppose that your receiver could handle 1 datagram every 2 seconds. And suppose that you had the delay here was 1. So thing is, for each individual link, where's the bottleneck in this system? Well, it's the thing that takes the longest amount of time to push forward one of these datagrams. Well, here it's all the same. It's 1, 1, 1. How long does it take the receiver to push one out? 2. It takes 2 seconds. So what that means is it's the bottleneck. So here what we're going to have is 2 times, and the round trip time is 1, 2, 3, 4, 5, 6. Just 1/2. And so the number that our window size is going to be here is 3. So what does that mean? Suppose that we started feeding things in at 1 datagram every 2 seconds into here, and we did 3 at a time. Then what we're going to do is at time t equals 0, we're going to have, so we put 1 in. So after 2 seconds, we have 1 here, right? Then we put the next one in. So then that means after 2 seconds, 1 is here and 1 is here, right? 2 seconds later, then we're over here, and then at that point, what you'll notice is that it becomes pretty apparent that the rate, a couple things. One is that the rate at which you're sending these is not congesting the receiver, right? Because it's being able to take these in and then send back ACKs, right? Process and then send back an ACK at the same rate that you're putting it in. But now that you've put these 3 in here, Notice that once the ACK comes back over here, you're ready to send another one. So now you can keep pumping these things out. If this ACK says, okay, I've received them all, then you can start sending another one as soon as you receive that last ACK, and you can maintain a high that maximum rate, the bottleneck rate of sending these out. This type of thing, you should probably work out a couple of examples, because it takes, if you practice with this a little bit, it'll become a little more intuitive. But try something simple like this. Try seeing what happens if you if you change these numbers here, and use this model where you put these datagrams on and see how they flow through, and think about this type of model where ideally what you want is this to be your window. The most time it takes for you to get a datagram over and an acknowledgement back. Okay, you might want to play with some of this, some of these examples in recitation with your TA, or if you have any questions on this, see me after class. We already talked about how we can change the window time. So ideally, what you want is if the network is going to be your bottleneck, as congestion patterns change, you want to be able to dynamically adapt your window size to make sure that your packets aren't being dropped. And the problem here, the big trade-off you face is that if you lose packets, you basically have to resend either that packet or potentially the whole window, because if you overflow if you congest imagine if you get congestion at the receiver side, right, and you're right at the beginning of a window, then everything else is probably going to have to be dropped if it's very congested. So the expense could be that you actually have to resend the whole window. So too large of a window could get you into trouble if there's a lot of reliability issues on the network.
It seems implicit in this little diagram that you've shown that we need to basically time release our messages or that are part of the window size to basically distribute them evenly over the round trip data time.
Yeah.
Is that how it happens in practice, or is that only the way it looks in this model?
That's the way it looks in this model. If you know something about the buffer size over here, you might want to send them all at once if the network can handle it. But typically, I mean, there is some time delay at the sending side for when you're going to send these, and it'll depend more on the specifics of the network as to how exactly whether you want to send things all at the same time or use the rate at the bottleneck, if you know the rate at the bottleneck, so that it becomes you have to do a little bit more analysis about what the specifics are. TCPIP does have some flow control built in, so you might want to grab a TCPIP paper and see how they actually implement it and think about these trade-offs and build up upon this model here.